During the Cold War, Sweden faced a terrifying possibility. If a global war ever erupted between the superpowers, the skies over northern Europe could become one of the first battlefields. Sweden was officially neutral, but geography placed it directly between two rival blocs. To the west were NATO countries, and to the east stood the enormous military power of the Soviet Union. Between them lay the Baltic Sea, a narrow stretch of water that, during the tense decades of the Cold War, became one of the most heavily monitored regions in the world. Radar stations lined the Scandinavian coastline, naval patrols crossed the cold northern waters, and military aircraft constantly flew along invisible borders in the sky. In such an environment, Sweden's neutrality did not mean safety. Instead, it meant the country had to be ready to defend itself alone if conflict suddenly erupted. The danger was not theoretical. Soviet military aircraft were regularly detected near Swedish airspace. Reconnaissance flights tested radar coverage and reaction times, while long-range bombers trained over the Arctic and Baltic regions. Swedish radar operators spent long hours staring at glowing screens, tracking aircraft moving slowly across the horizon. Most of the time, those aircraft remained outside Swedish territory. But in the event of war, those same aircraft could appear suddenly over the sea, heading directly toward Swedish cities and military installations. If that happened, Sweden would have only minutes to react. The difference between success and disaster would depend entirely on how quickly interceptor aircraft could take off and climb into the sky. Among the most feared aircraft flying near Sweden was the Tu-95, a massive long-range bomber designed to carry nuclear weapons across continents. With its huge swept wings and 4 enormous turboprop engines, the Tu-95 could fly thousands of kilometers without refueling. Its range allowed it to patrol vast areas of the Arctic and North Atlantic, and its speed meant that it could reach targets deep inside Europe before defenders even realized what was happening. Another aircraft frequently seen on radar screens was the Tu-16, a fast jet-powered bomber capable of carrying both conventional and nuclear weapons. Compared to earlier propeller-driven bombers, the Tu-16 represented a new level of speed and striking power. Together, these aircraft symbolized a terrifying reality of the Cold War. Strategic bombers could deliver devastating attacks across huge distances with very little warning. For Swedish military planners, the implications were clear. If Soviet bombers ever crossed the Baltic Sea during a crisis, the country would have only one chance to stop them: intercept them before they reached their targets. That requirement created enormous pressure on Sweden's air defense system. Fighter aircraft had to launch within minutes of receiving an alert. They had to climb rapidly to high altitude, locate the incoming bombers using radar, and destroy them before they could release their weapons. Every second counted. A delay of even a few minutes could mean the difference between intercepting the bombers over the sea or allowing them to reach populated areas. But there was another problem. Sweden could not rely on large foreign alliances for protection. Unlike many European countries, Sweden was not a member of NATO. It also had no intention of joining the Warsaw Pact. Instead, the Swedish government pursued a policy of armed neutrality. This meant the country would remain politically independent, but it also meant that Sweden had to build its own powerful defense forces capable of resisting invasion or attack without outside help. As a result, the Swedish military invested heavily in domestic weapons development, particularly in aviation. The Swedish Air Force became one of the largest and most advanced air forces in Europe relative to the country's population. By the early 1950s, Swedish defense planners realized that the next generation of fighter aircraft would need to be dramatically more capable than anything they currently operated. Older fighters were simply too slow to intercept modern jet bombers effectively. New aircraft would need to fly faster than the speed of sound, climb extremely quickly, and operate in harsh Nordic conditions. They would also need to function from dispersed airfields, since large centralized airbases could easily be destroyed during the opening hours of a war. Designing such an aircraft would not be easy, In fact, many experts believed it might be impossible to meet all of these requirements at once. Yet Sweden had one major advantage: its domestic aerospace industry. The company Saab AB had already developed several successful military aircraft and was rapidly expanding its capabilities. Swedish engineers were ambitious and willing to experiment with unconventional ideas if it meant achieving a decisive advantage in air defense. When the Swedish Air Force issued its requirement for a new high-speed interceptor, Saab engineers began searching for solutions that no one else had attempted before. The challenge they faced was enormous. The aircraft had to fly at speeds approaching Mach 2, climb faster than any bomber it might encounter, and remain stable at both low and extremely high speeds. Achieving these goals required radical thinking about aerodynamics, particularly the design of the aircraft's wings. Traditional fighter designs were beginning to reach their limits, and engineers realized that entirely new shapes might be necessary to achieve the required performance. The solution they eventually developed would look unlike almost any fighter aircraft ever built. Instead of a conventional wing shape, the new Swedish interceptor would use a radical configuration consisting of two large triangular wings joined together in a single structure. The design looked strange, almost alien compared to other aircraft of its time. But according to the engineers who created it, this unusual shape could provide exactly the combination of speed, stability, and maneuverability needed to defend Sweden's skies. That aircraft would eventually become known as the Saab 35 Draken. Its name meant dragon in Swedish, and like the mythical creature, it would become one of the most distinctive and formidable aircraft of the Cold War era. But before the Draken could take to the skies, Sweden first had to solve a series of engineering challenges that would push the limits of aerodynamics and aircraft design. In the early years of the Cold War, Sweden understood something many other countries did not. Modern war would move extremely fast. Jet aircraft, long-range missiles, and nuclear weapons meant that traditional defenses could collapse within hours. Large military bases, once considered the backbone of national defense, were suddenly vulnerable. A single nuclear strike or a coordinated bomber attack could destroy an entire air force while its aircraft were still sitting on the ground. For Sweden, this was an unacceptable risk. If the country hoped to maintain its independence between two rival military blocs, it needed a defense strategy that could survive the first strike of a modern war. Unlike many nations in Western Europe, Sweden did not join NATO. At the same time, it remained firmly outside the influence of the Soviet Union and the Warsaw Pact. Instead, Sweden pursued a policy often described as armed neutrality. The idea was simple but demanding. Sweden would stay politically neutral in international conflicts, but it would maintain a powerful military capable of defending the country alone if necessary. This approach required enormous investment in domestic industry, advanced technology, and military planning. The Swedish government believed that if the nation could demonstrate the ability to resist invasion, it would discourage both sides of the Cold War from turning the country into a battlefield. One of the most important elements of this strategy was air defense. Sweden's geography made control of the skies absolutely critical. The country's long coastline faced the Baltic Sea, a region filled with military bases and aircraft belonging to both NATO and Warsaw Pact forces. Enemy bombers approaching from the east could cross the sea quickly and reach Swedish territory in minutes. That meant the Swedish Air Force had to be ready to respond instantly. Fighters needed to launch rapidly, intercept incoming aircraft over the sea, and destroy them before they reached their targets. However, there was a major problem with relying on traditional air bases. Large airfields with long runways were easy to find on reconnaissance photographs and easy to destroy with bombs or missiles. Swedish planners realized that if their aircraft were concentrated at a few major bases, those bases would become the first targets of any enemy attack. Once destroyed, the Air Force would have no way to respond. The solution was radical but brilliant. Disperse the entire Air Force across the country. Instead of relying only on permanent bases, Swedish aircraft would operate from dozens of small, hidden airstrips scattered through forests, remote fields, and even sections of public highways. This concept eventually became known as the BAS-60 system, a decentralized air-based network designed specifically for the realities of modern air warfare. Under this system, fighter aircraft could land, refuel, rearm, and take off again from temporary locations, rather than returning to large central bases. Sections of highway were specially reinforced so that jets could use them as emergency runways. Nearby forests concealed maintenance vehicles, fuel trucks, and ammunition supplies. Small teams of ground crews trained to service aircraft quickly under difficult conditions, sometimes in freezing temperatures or poor weather. The idea was that even if enemy forces destroyed several airfields, dozens of other operating locations would still remain active. Enemy intelligence would have enormous difficulty locating every aircraft, and Swedish fighters could continue launching intercept missions even after heavy attacks. This strategy placed unusual demands on aircraft design. Fighter jets normally require long, carefully maintained runways and extensive ground support equipment. Operating from highways or small remote strips was extremely challenging. Aircraft would need strong landing gear, reliable engines, and the ability to take off quickly from short distances. Maintenance procedures also needed to be simple enough that small ground crews could perform them in the field. In other words, Swedish fighters could not be designed only for maximum performance in the air. They also had to function in a highly decentralized and rugged operational environment. By the mid-1950s, the Swedish Air Force had already begun expanding into one of the largest air forces in Europe, relative to the country's population. Hundreds of aircraft protected Swedish airspace, and new radar systems extended detection ranges across the Baltic region. But technology was advancing quickly, and the rise of high-speed jet bombers created new challenges. Older fighters simply could not climb fast enough or fly high enough to intercept modern bomber formations. If Sweden wanted to maintain credible air defense, it needed a new generation of interceptor aircraft capable of responding faster than anything before. That requirement led directly to one of the most ambitious aviation projects in Swedish history. The government turned to the country's leading aerospace manufacturer, Saab AB, and asked its engineers to design a fighter that could meet these extraordinary demands. The aircraft would need to launch quickly from dispersed bases, climb rapidly to high altitude, and reach speeds approaching Mach 2 in order to intercept enemy bombers before they crossed Swedish territory. At the same time, it had to remain stable at lower speeds so that it could safely operate from shorter runways, such as those found on highways or small emergency airfields. For engineers, this was an incredibly complex challenge. High-speed aircraft often sacrifice low-speed handling in order to achieve greater top speed. Designing a fighter that could perform well at both extremes required new aerodynamic ideas and bold experimentation. Traditional wing designs might not be enough. Saab's engineering teams began exploring unusual shapes and configurations that could provide both stability and speed. What they eventually developed would become one of the most recognizable aircraft designs of the Cold War. Its wings would form a distinctive double triangle shape unlike anything flying at the time, a design that would allow the aircraft to operate effectively across a wide range of speeds. That experimental aircraft would later become the Saab 35 Draken. But before the Draken could defend Sweden's skies, Saab engineers first had to confront one of the greatest engineering puzzles in aviation: how to build an interceptor fast enough to chase down modern bombers while still capable of operating from the unusual and decentralized air bases that define Sweden's strategy for survival. In solving that puzzle, they would create a fighter unlike any other aircraft of its era. By the early 1950s, Sweden's defense planners understood that the next phase of air warfare would be defined by speed. The arrival of jet bombers, capable of flying higher and faster than earlier aircraft, meant that traditional fighter designs were rapidly becoming obsolete. If Sweden hoped to maintain control of its airspace, it needed a new type of interceptor, an aircraft capable of launching quickly, climbing to high altitude in minutes, and reaching enemy bombers before they could release their weapons. This mission would require an aircraft far more advanced than anything Sweden had built before. The responsibility for creating such a machine fell to the country's leading aerospace company, Saab AB, whose engineers had already proven their ability to design innovative aircraft under extremely demanding conditions. At Saab's design offices in Linköping, a team of engineers began studying the requirements issued by the Swedish Air Force. The list was ambitious, almost intimidating. The new aircraft needed to reach speeds approaching Mach 2, climb rapidly enough to intercept high-altitude bombers, carry radar-guided missiles, and operate reliably in harsh Nordic weather conditions. At the same time, the aircraft had to be rugged enough to function from Sweden's dispersed airbase network, including highway runways and small remote strips created under the Boss 60 defense system. In practical terms, this meant the aircraft had to combine extreme high-speed performance with stable, low-speed handling, two characteristics that are normally very difficult to achieve in the same design. Leading the project was Swedish aerospace engineer Eric Bratt, who understood that traditional design approaches might not be enough to meet these demands. Bratt and his colleagues carefully studied the aerodynamics of existing jet fighters around the world. Aircraft such as the MiG-21 and the F-100 Super Sabre demonstrated that delta wings, triangular wings with a swept shape, could provide stability and efficiency at supersonic speeds. However, delta wings also introduced challenges. At lower speeds, particularly during landing, aircraft with large delta wings could be difficult to control. Long runways were often required, and pilots needed special training to manage the aircraft safely during takeoff and landing. For Sweden, whose aircraft might need to operate from highway strips or small emergency bases, this was a serious problem. Bratt's team faced a dilemma. To intercept high-speed bombers, the aircraft needed a wing optimized for supersonic flight. But to operate from dispersed bases, the aircraft also needed good low-speed characteristics and stable handling. The engineers spent countless hours analyzing wind tunnel data, testing scale models, and exploring alternative wing shapes that could provide the right balance between speed and stability. Conventional solutions seemed inadequate. Every design that improved supersonic performance created new difficulties during takeoff or landing. Conversely, designs that improved low-speed handling often reduced the aircraft's ability to reach Mach 2. During this period of experimentation, Saab engineers began exploring a concept that had rarely been attempted before. Instead of using a single triangular delta wing, they considered combining two different delta shapes into one continuous wing structure. The front portion of the wing would have a sharper angle designed to improve airflow control at lower speeds, while the outer section would maintain the larger sweep required for high-speed flight. In theory, this unusual configuration could allow the aircraft to perform well across a much wider range of speeds. At low speeds, the inner section of the wing would help maintain stability and lift. At supersonic speeds, the outer wing would reduce drag and allow the aircraft to accelerate toward Mach 2. To many engineers at the time, the concept sounded risky. Aircraft design in the 1950s was still evolving rapidly, and pushing aerodynamic boundaries could easily lead to instability or unpredictable behavior. Nevertheless, Saab's leadership believed that innovation was necessary if Sweden wanted to maintain technological independence in aviation. Wind tunnel experiments began using scale models with this unusual double delta configuration. Early tests revealed promising results. Airflow across the wing remained stable over a wide range of speeds, and the design appeared capable of delivering both the high-speed efficiency required for interception and the low-speed stability necessary for dispersed operations. Encouraged by these findings, Saab moved forward with the design. The aircraft would eventually receive the designation Saab 35 Draken, a name that translated to dragon. The choice of name was fitting. Just as a dragon in mythology combined power and agility, the new interceptor was intended to combine speed, altitude performance, and operational flexibility in a single aircraft. Yet the Draken's distinctive shape also made it immediately recognizable. Its wing configuration, formed by two overlapping triangular sections, looked dramatically different from other fighters of its era. Designing the aircraft was only the first step. Turning that radical concept into a real flying machine required solving countless engineering challenges. Structural strength had to be carefully balanced against weight, since the aircraft needed powerful engines to reach supersonic speeds. The landing gear had to withstand operations from rough or temporary airstrips. Advanced radar and missile systems needed to be integrated into a relatively compact airframe. Every component, from the fuselage structure to the cockpit instrumentation, had to support the aircraft's role as a high-speed interceptor, ready to scramble at a moment's notice. Despite these challenges, Saab engineers pushed forward with determination. The Swedish government viewed the project as a critical element of national defense, and resources were allocated to ensure its success. Engineers, technicians, and test specialists worked together to transform experimental wind tunnel models into full-scale prototypes. By the mid-1950s, the first prototype airframe was nearing completion, representing years of theoretical work and aerodynamic research. Soon, the radical design would face its greatest test, leaving the ground for the first time. The upcoming test flights would determine whether Saab's bold ideas were truly viable. If the aircraft performed as predicted, Sweden would possess one of the most advanced interceptor fighters in Europe. But if the design failed, the country could find itself dangerously vulnerable during a period when Cold War tensions were already pushing global aviation technology to its limits. The fate of Sweden's future air defense now rested on the success of an aircraft that many observers believed looked too unusual to ever work. Designing a supersonic interceptor in the 1950s was not simply a matter of adding a more powerful engine. Once an aircraft approached the speed of sound, entirely new aerodynamic problems began to appear. Airflow around the wings behaved differently. Shockwaves formed along the aircraft's surface, and even small design mistakes could make an aircraft unstable or impossible to control. Engineers around the world were racing to understand how to build aircraft capable of flying beyond Mach 1. And every country experimenting with supersonic flight faced the same fundamental challenge: how to design wings that could function efficiently at both low and extremely high speeds. For Sweden's new interceptor project, this challenge was particularly severe. The aircraft needed to reach speeds approaching Mach 2 in order to intercept modern bombers. But unlike many other supersonic fighters, it also needed to take off and land from relatively short runways under the country's dispersed airbase system. High-speed aircraft normally used thin, highly swept wings designed to minimize drag at supersonic speeds. However, those same wings often produced very little lift at low speeds, forcing pilots to use long runways and very careful landing procedures. Such limitations were unacceptable for an aircraft expected to operate from improvised bases or highway runways across Sweden. This is where Saab's engineers made a decision that would define the aircraft forever. Instead of using a conventional wing, they developed an entirely new configuration known as the double delta wing. At first glance, the concept looked almost too strange to work. The wing consisted of two triangular sections connected together. The inner portion had a steep angle and generated strong lift at lower speeds, helping the aircraft remain stable during takeoff and landing. The outer portion was shaped differently, optimized for supersonic airflow and reduced drag at high speed. Together, these two sections formed a distinctive, diamond-like shape when viewed from above. The idea behind this configuration was simple in theory, but extremely complex in practice. At low speeds, airflow over the inner section of the wing would generate powerful vortices, spiraling streams of air that helped maintain lift even when the aircraft approached a stall. These vortices improved control and stability, allowing the aircraft to operate safely at slower speeds than most supersonic fighters. As the aircraft accelerated toward supersonic speeds, the outer wing sections would begin to dominate the aerodynamic behavior of the aircraft, reducing drag and improving efficiency at high altitude and high velocity. To verify that this unusual design could actually work, Saab engineers conducted extensive wind tunnel testing. Scale models of the aircraft were placed inside high-speed airflow tunnels, where sensors measured pressure, turbulence, and lift across the wing surface. Engineers carefully observed how air moved across the different sections of the wing at various speeds and angles of attack. The results were encouraging. Not only did the double delta configuration produce stable airflow at high speed, but it also created strong vortex lift that improved low-speed performance. In effect, the wing allowed the aircraft to behave like two different fighters depending on its speed. Despite these promising results, the design remained controversial. Some engineers worried that the unusual wing shape might create unpredictable handling characteristics in real flight. Supersonic aircraft design was still a relatively new science, and unexpected aerodynamic effects could easily appear once a full-scale aircraft left the ground. Nevertheless, the potential advantages were too significant to ignore. If the design worked as predicted, Sweden would gain an interceptor capable of combining Mach 2 performance with the ability to operate from dispersed bases, a combination that few aircraft in the world could achieve. As construction of the prototype progressed, the aircraft's distinctive appearance became impossible to ignore. Compared with other fighters of the era, the new Swedish interceptor looked almost futuristic. Most jet fighters used swept wings or single delta wings, but the new design appeared to have two separate triangular wings fused together. Observers who saw the aircraft for the first time often described it as strange, unconventional, or even alien in appearance. Yet, behind this unusual shape lay a carefully engineered aerodynamic solution to one of the most difficult problems in aircraft design. The aircraft would soon receive its official name, the Saab 35 Draken. In Swedish, Draken means dragon, a name that reflected both the aircraft's aggressive appearance and its intended role as a powerful guardian of Swedish airspace. The dragon imagery also captured something about the aircraft's personality. Like the mythical creature, the Draken was fast, powerful, and slightly mysterious. Its unique wing shape gave it capabilities that few other aircraft possessed, but it also meant that pilots and engineers would need to understand its behavior very carefully. By the time the prototype was ready for flight testing, Saab engineers had already invested years of research into the double delta concept. Wind tunnel experiments suggested the aircraft should perform well across a wide range of speeds, but real flight would reveal whether those predictions were accurate. As with many experimental aircraft of the era, the first test flights carried significant risks. Supersonic aerodynamics could behave unpredictably, and new aircraft designs sometimes revealed hidden flaws only after leaving the ground. Nevertheless, the moment of truth was approaching. In 1955, the first prototype of the Draken prepared for its maiden flight. Engineers, technicians, and test pilots gathered to watch as the strange new interceptor taxied onto the runway. The aircraft represented the culmination of Sweden's ambitious attempt to build one of the most advanced fighters in Europe. If the double delta wing worked as intended, the Draken would become a revolutionary interceptor capable of defending Sweden's skies during one of the most dangerous periods of the Cold War. But if the design failed, years of work and a critical piece of Sweden's air defense strategy could collapse in a single moment. By the mid-1950s, years of aerodynamic research, wind tunnel testing, and engineering work had finally produced a full-scale prototype of Sweden's radical new interceptor. The aircraft looked unlike almost anything flying at the time. Its distinctive double triangle wing gave it a sharp, futuristic silhouette, and even experienced aviation engineers were unsure exactly how it would behave once it left the ground. But the time for theory had passed. Now the aircraft had to prove itself in real flight. In 1955, the prototype of what would become the Saab 35 prepared for its maiden flight, marking one of the most important moments in Sweden's aviation history. Test pilots approached the aircraft with a mixture of excitement and caution. Experimental aircraft always carried risk, especially during an era when supersonic aerodynamics were still being understood. The aircraft's unusual wing shape promised exceptional performance, but it also raised questions about stability and control. When the Draken accelerated down the runway for the first time, engineers and technicians watched carefully, hoping that years of theoretical calculations would translate into stable flight. As the aircraft lifted from the ground and climbed into the sky, the initial results were promising. The prototype demonstrated strong acceleration, responsive controls, and stable flight characteristics at moderate speeds. For Saab engineers, the successful first flight confirmed that their bold aerodynamic concept was viable. However, early test flights soon revealed that the aircraft also had a number of unexpected behaviors. One of the most concerning issues appeared when the aircraft slowed down during landing approaches. At certain angles of attack, the aircraft could suddenly lose lift in a dramatic aerodynamic stall. Instead of gradually losing altitude like most aircraft, the Draken sometimes entered a sharp nose-up position before dropping rapidly. This phenomenon became known among test pilots as a superstall. For pilots unfamiliar with the aircraft, the situation could be extremely dangerous. Recovering from such a stall required precise control inputs and a clear understanding of the aircraft's aerodynamic behavior. Despite the alarming nature of the superstall, engineers quickly realized that the phenomenon was connected to the same aerodynamic features that made the double delta wing effective. The powerful vortex airflow generated by the wing could sometimes destabilize the aircraft when the angle of attack became too high. However, once pilots learned how to manage the aircraft properly, the Draken often recovered from these stalls surprisingly quickly. In fact, the aircraft's ability to briefly enter extremely high angles of attack without losing complete control would later become one of its most distinctive flight characteristics. Decades later, similar high-angle maneuvers would become famous in aircraft like the Sukhoi Su-27, which could perform the dramatic maneuver known as Pugachev's Cobra. While the Draken was not originally designed for aerobatic displays, its unusual aerodynamics meant that it could briefly achieve comparable flight attitudes under certain conditions. Test pilots spent countless hours learning how the new aircraft behaved across its full flight envelope. Flights were conducted at progressively higher speeds and altitudes as engineers gathered data on the aircraft's performance. One of the most critical milestones was achieving supersonic flight. As the Draken accelerated beyond the speed of sound, the aerodynamic characteristics predicted during wind tunnel testing began to appear. Shockwaves formed along the wing edges, and the aircraft's drag profile changed as it moved into the supersonic regime. Encouragingly, the aircraft remained stable, confirming that Saab's double delta design was capable of operating effectively at very high speeds. Engine performance also played a critical role in these tests. The aircraft needed enough thrust to accelerate quickly and climb rapidly during interception missions. Engineers closely monitored engine temperatures, fuel consumption, and structural stresses on the airframe as the aircraft pushed toward higher speeds. Each successful test flight expanded confidence that the Draken could meet the demanding requirements set by the Swedish Air Force. Yet testing remained cautious. Supersonic aircraft of the era often encountered unexpected structural or aerodynamic issues during development, and engineers carefully analyzed every piece of data collected during the flights. Gradually, the Draken's reputation among test pilots began to change. What initially seemed like a risky experimental design started to reveal itself as a remarkably capable interceptor. The aircraft could accelerate rapidly, climb to high altitude quickly, and maintain stability even at extreme speeds. Pilots also discovered that once they understood its handling characteristics, the aircraft was surprisingly agile for an interceptor. The powerful vortex lift created by the double delta wing allowed the aircraft to perform tight turns and maintain control at angles of attack that would have stalled many other fighters. As testing continued, Saab engineers made a series of improvements to refine the aircraft's handling. Adjustments were made to control surfaces, flight procedures, and pilot training methods to ensure that the aircraft could be operated safely by frontline pilots. These modifications gradually eliminated the most dangerous aspects of the superstall phenomenon and made the aircraft far more predictable during landing approaches. By the late stages of testing, confidence in the aircraft had grown significantly. What once looked like a strange experimental machine was now proving itself to be one of the most advanced interceptor designs in Europe. The success of these early flight tests marked a turning point for Sweden's air defense strategy. The Draken was no longer just an engineering experiment. It was becoming a practical operational aircraft capable of defending Swedish airspace against high-speed bombers. Its distinctive shape, once viewed with skepticism, had proven to be a powerful aerodynamic solution. With continued development and production, the aircraft would soon enter service with the Swedish Air Force and begin its role as one of the most important guardians of the country's skies during the tense decades of the Cold War. By the early 1960s, the long development process had finally reached its conclusion. The experimental interceptor that had once seemed so unusual was now ready to enter operational service. The Saab 35 Draken officially joined the Swedish Air Force and quickly became one of the most advanced fighters in Northern Europe. Its mission was clear and uncompromising: defend Swedish airspace and intercept any hostile aircraft approaching the country. In the tense atmosphere of the Cold War, this mission was taken extremely seriously. Every radar detection over the Baltic Sea had the potential to trigger an interceptor scramble, and Draken pilots were trained to respond within minutes. The aircraft's performance made it ideal for this role. Capable of reaching speeds around Mach 2, the Draken could climb rapidly toward high-altitude targets and close the distance with incoming aircraft before they reached Swedish territory. Its powerful radar systems allowed pilots to detect and track targets even in poor weather or darkness, while guided air-to-air missiles provided the firepower needed to destroy large bomber aircraft. During interception exercises, Draken pilots practiced scrambling from their bases, climbing to high altitude at maximum speed, and positioning themselves ahead of simulated enemy bombers. These exercises were designed to mirror the scenario Swedish planners feared most: Soviet bombers crossing the Baltic Sea toward Scandinavian targets. Operating the Draken also required pilots to master the aircraft's unique flight characteristics. The double delta wing gave the aircraft remarkable performance across a wide range of speeds, but it also demanded precise handling during certain maneuvers. Swedish pilots underwent extensive training to learn how to manage the aircraft's high angle of attack behavior and to safely recover from unusual flight attitudes. Once mastered, however, the aircraft proved to be both powerful and surprisingly agile. Its ability to generate vortex lift allowed it to maintain control even during aggressive turns or rapid climbs, making it far more maneuverable than many interceptors of the era. One of the most distinctive aspects of the Draken's service life was its role within Sweden's dispersed airbase network. Instead of operating only from large, permanent airfields, Draken squadrons frequently trained to use sections of reinforced highways as emergency runways. In the event of war, aircraft could disperse across dozens of hidden operating locations, reducing the risk that a single enemy attack could destroy the entire fleet. Ground crews practiced rapid refueling and rearming procedures so that aircraft could be returned to the air as quickly as possible. In many cases, a small team of technicians could prepare a Draken for another sortie within minutes, allowing the interceptor force to maintain continuous readiness even during sustained operations. The aircraft's presence in Swedish skies became a constant reminder of the country's determination to defend its neutrality. Draken fighters regularly patrolled airspace over the Baltic Sea, monitoring aircraft approaching Swedish territory. Radar stations across the country worked closely with interceptor squadrons to coordinate responses to unidentified aircraft. When radar operators detected a potential intrusion, Draken pilots could be ordered to scramble immediately, racing toward the target at supersonic speed. Although many of these missions ended without confrontation, they demonstrated that Sweden possessed a capable and responsive air defense system. Throughout the 1960s and 1970s, the Draken remained the backbone of Sweden's interceptor force. Continuous upgrades improved radar equipment, avionics, and weapons systems, ensuring that the aircraft remained effective even as aviation technology evolved. New missile systems increased the aircraft's ability to engage targets at longer ranges, while improved electronic systems enhanced its ability to detect and track incoming aircraft. Despite its unusual appearance, the Draken proved itself to be reliable and adaptable, serving effectively for decades in a rapidly changing technological environment. The aircraft's distinctive silhouette also became one of the most recognizable shapes in military aviation. The sharp double delta wings gave the aircraft an aggressive profile that stood out immediately against the sky. Aviation enthusiasts and military observers often describe the aircraft as futuristic, a design that seemed ahead of its time compared with many contemporary fighters. Yet the Draken's unusual appearance was not merely aesthetic. It was the direct result of the aerodynamic innovation required to meet Sweden's unique defense needs. For Swedish pilots, flying the Draken represented both a privilege and a responsibility. They understood that their aircraft formed the first line of defense against any threat approaching the country. Training exercises were intense and realistic, often simulating high-speed interceptions against bomber formations. Pilots practiced navigating difficult weather conditions, coordinating with radar controllers, and launching missiles against fast-moving targets. The goal was to ensure that if a real threat ever appeared, Sweden's interceptor force would respond instantly and effectively. As the decades passed, newer aircraft would eventually begin replacing the Draken in Swedish service. However, during its operational peak, the aircraft played a crucial role in maintaining the security of Swedish airspace. It demonstrated that a relatively small country could design and operate advanced military aircraft capable of competing with the technology of much larger powers. The Draken's success also laid the foundation for future Swedish fighter designs, proving that bold aerodynamic innovation could produce both high performance and operational flexibility. By the time the aircraft approached the later stages of its service life, the Draken had firmly established itself as one of the most distinctive and capable interceptor aircraft of the Cold War era. It had defended Swedish skies for decades, participated in countless training missions, and shown that unconventional engineering could produce extraordinary results. Yet the story of the Draken did not end with Sweden alone. In the years ahead, this unusual fighter would spread beyond Scandinavian borders, serving with several other air forces and leaving a lasting mark on the history of military aviation. By the late decades of the Cold War, the Saab 35 Draken had already proven itself as one of the most distinctive fighter aircraft in Europe. What began as an experimental solution to Sweden's unique defense problems had evolved into a mature and reliable interceptor. Its unusual double delta wing, once considered risky and unconventional, had demonstrated clear advantages in both high-speed interception and operational flexibility. As the aircraft matured, it began attracting interest beyond Sweden's borders, and several other countries soon adopted the Draken as part of their own air defense forces. Among the first nations to operate the Draken were Sweden's Nordic neighbors. Both Denmark and Finland integrated the aircraft into their air forces, recognizing its effectiveness as a high-speed interceptor capable of protecting national airspace during a period of intense geopolitical tension. In these countries, the Draken served a similar role to its mission in Sweden: rapid response to unidentified aircraft approaching national borders. Pilots trained extensively to intercept potential intrusions, often operating in harsh weather conditions over the Baltic Sea and surrounding regions. The aircraft's reliability and speed made it particularly well suited to this demanding task. Further south, the aircraft also found a long-term home in Austria, where it served as one of the country's primary air defense fighters for many years. Austrian Draken pilots became well known for their skill in operating the aircraft within mountainous terrain and complex airspace environments. Despite being designed decades earlier, the aircraft continued to perform effectively thanks to upgrades in avionics, radar systems, and weaponry. Its long service life demonstrated the strength of the original aerodynamic design, which remained competitive even as aviation technology evolved rapidly throughout the Cold War. One of the most remarkable aspects of the Draken's legacy was its influence on later Swedish fighter development. The success of the double delta concept encouraged Saab engineers to continue experimenting with innovative aerodynamic solutions. Lessons learned from the Draken program contributed directly to the development of its successor, the Saab 37 Viggen, an advanced multi-role aircraft that incorporated canard wings and powerful new avionics systems. The Viggen expanded Sweden's air combat capabilities significantly, adding ground attack and reconnaissance roles while maintaining strong interceptor performance. Decades later, Saab would once again build on this tradition of innovation with the Saab JAS 39 Gripen, a modern fighter designed for flexibility, efficiency, and advanced electronic warfare capabilities. Like the Draken before it, the Gripen was built with Sweden's unique defense strategy in mind. It could operate from dispersed bases and highway runways, continue flying even if major airfields were destroyed, and respond quickly to threats approaching Swedish airspace. In many ways, the Gripen represented the modern evolution of ideas first explored during the Draken program. Although newer aircraft eventually replaced the Draken in frontline service, the aircraft's reputation continued to grow among aviation enthusiasts and historians. Its distinctive shape made it instantly recognizable at air shows and museums around the world. The sharp triangular wings and sleek fuselage gave the aircraft an appearance that still feels futuristic even decades after its introduction. For many observers, the Draken represents one of the most visually striking aircraft designs ever created. Beyond its appearance, the Draken also symbolizes an important moment in aviation history. During the Cold War, many countries relied heavily on aircraft developed by larger military powers. Sweden, however, chose a different path. By investing in domestic aerospace engineering and encouraging innovative design solutions, the country created a fighter aircraft that could compete with those produced by far larger nations. The Draken demonstrated that creativity, technical expertise, and strategic thinking could allow a smaller country to achieve remarkable technological achievements. Pilots who flew the Draken often described it as both challenging and rewarding. Its unique aerodynamic behavior required careful handling and a deep understanding of the aircraft's flight characteristics. Yet once mastered, the aircraft offered impressive performance and agility. Many pilots appreciated the aircraft's responsiveness and the sense of power it delivered during high-speed interceptions. These qualities helped cement the Draken's reputation as a formidable interceptor capable of defending national airspace under demanding conditions. Today, surviving examples of the Draken can still be seen in aviation museums and occasional airshow demonstrations. When the aircraft takes to the sky, its distinctive silhouette instantly captures attention, reminding viewers of a time when engineers pushed the boundaries of aerodynamics in pursuit of national security. The aircraft stands as a testament to the ingenuity of the engineers at Saab AB, whose willingness to experiment with unconventional ideas resulted in one of the most unique fighters of the 20th century. Looking back, the Draken's story reveals an important lesson about innovation in aviation. Sometimes the solutions to complex engineering challenges require designs that appear strange or unconventional at first glance. What matters is whether those designs ultimately solve the problem they were created to address. In the case of the Draken, The unusual double delta wing provided exactly the combination of speed, stability, and flexibility that Sweden needed during one of the most dangerous periods of modern history. In the end, the aircraft fulfilled its mission perfectly. For decades, the Draken stood ready to defend Swedish skies against any threat that might appear over the Baltic Sea. It served not only as a powerful interceptor, but also as a symbol of Sweden's determination to remain independent and secure during the uncertain years of the Cold War. The Draken had proven that sometimes the strangest ideas can lead to the most remarkable achievements in aviation.